So today we're going to talk about facility location, and that's going to segue nicely for us into network design that we're going to intro next lecture. So we'll start by looking at what are some of the factors, the broad factors that affect network design and facility location. We will look at some of the facility location problems. I think we'll probably start with the first few. And we'll see how we can use different heuristics and algorithms for solving these. So a little bit of a historical context. We'll look at two theories, starting with Weber's classification of theories of industries. So we have, for example, Weber, who classified industries as either weight losing, weight gaining, or weight neutral. In other words, weight sustaining. So if an industry is weight losing, everybody understands what a weight losing industry is? Other the industry goes on diet, but what is the meaning of weight losing? As you go through the production process, yes, it refines, you take out raw materials, that the weight becomes smaller, exactly. So you have a lower weight, okay? Agricultural products, mining products, most mining, petroleum refining would be weight-losing industries. Then you have the weight-gaining industries. Examples of weight-gaining industries. Automobile, right? You have small components coming in, they're light, then you assemble them together, and then they become a bigger product, and then you have a heavier product at the end of it, right? And then weight-sustaining, right? So you have, for example, dairy production, right? You have milk coming in, you pasteurize it, and it goes out. Orange juice is weight. Again, if you have orange juice coming in, right, or you have carbonated drinks coming in, they're basically the same weight as what's going out. You're not really losing too much in the process. So what is the purpose of classifying these? If you think about it in terms of transportation costs, if your higher transportation costs are going to be on the inbound side, you want to locate closer to the supplier. If your higher transportation costs are on the outbound side, you want to locate closer to the customer, right? So that's the basic premise behind this classification. Very simple, right? Now, Hoover's tapered transportation rates took this a little bit further and said, okay, now if you locate close to your supplier, and if you look at your inbound transportation, which is that blue line, your transportation costs are going to be the lowest. But then as you locate further and further away, your inbound transportation costs are going to go higher, right? Similarly, for your outbound transportation costs, the further you away from your customer, the higher transportation costs, and they keep going to go lower and lower. Therefore, if you add up your inbound and outbound transportation costs, you get this total transportation cost line, which tells you what? Where do you want to locate? Sorry? Where they cross, this is going to be the maximum transportation, right? That's maximum, that's the highest transportation cost. Either closer to the consumer or closer to the supplier, right? So these were sort of basic facility location fundamentals that, you know, economists came up with 100 years ago. However, if you look at transportation networks today, where does FedEx have its hub? Its global hub? Memphis, right? Memphis, Tennessee. Where does UPS have its global hub? Louisville. Just a wild guess. Okay, I don't expect you to know this. Which airport has the highest volume of freight moving through it every year? Anchorage, exactly. Very good. Impressive. So, why Anchorage? It's closest point to 80% of the world's population, right? So, Anchorage, great circle flight. You can go to any part of the world. 80% of the population in the shortest time. So it's a major hub for global air freight. Okay, so obviously, those areas are neither close to a supplier nor close to a customer. But now we have, if you think about yourself as, say, Dow Chemical, your plant is in Midland, Michigan. You're routing freight even if you're sending by Northwestern, all right, or Northwest Freight, or if you're sending by Air Alaska. It's going probably from Detroit to Anchorage, and Anchorage to wherever else in the world it's going to. Yeah? So why do we have these major global hubs located where they are? If you think about transportation economics, 150, 100 years ago, you had linear markets. You had manufacturers basically doing business in linear markets, in single lanes, maybe 2 or 3 different lanes, where these sort of theories made sense, anecdotally, maybe even analytically. But now if you look at today's market, the market is the globe, right? You produce globally, you consume globally. So all of these don't matter. I mean, Columbus, Ohio is within 500 miles of all of North America's consumption, of 80% of, or 60% of North America's consumption. Next week I'm going to give a talk, and I did an analysis, and I did the same thing. West Virginia is within 40% of the U.S.'s population, within one day's drive of 40% of U.S. population. Within 60%, within 1.5 days of 60% of the U.S. population, right? So location is an important factor. This is on the consumer side, but what about the demand side, on the supply side? So one of the reasons we're going to have this conference next week is for the majority of the chemical industry, all of the feedstocks, that is all of the natural gas inputs that go into making all the chemicals that we use every day, 95% of it comes from the Gulf Coast, Louisiana and Gulfport. But now we're sitting on the Marcellus and Utica shale, which is probably going to grow this region into a competitor with the Gulf Coast, as a result of which transportation economies are going to change, right? So what's the opportunities that we have for new supply chain companies or new downstream industrial manufacturers coming and locating here in West Virginia, Kentucky, and Ohio? So these laws of transportation worked at one time, but today they don't really work because we live in a global economy. You can produce anywhere in the world and consume anywhere in the world, but still the fundamentals remain the same. The fundamentals still are, you want to be close to your customer, but you also want to be close to your supplier. And that's one of the great strengths that we have here in West Virginia, is we can be close to the supply of shale gas and ethane liquids and be close to the customer as well. So we also have to think about what are the other factors driving facility location. We know that customer service is an important part of supply chain and logistics. An important part of enabling customer service is access to transportation. We can see that freight rates will influence the company's use of various modes of transportation. If air freight was the cheapest, we would all use air freight, right, for all of our needs, whether it was for shipping or for transportation. Then we know that taxes are an important part of businesses' cost of doing business in any location. We saw that with the debate in the government, in Congress, and also the passage of the latest tax breaks that we saw last year. The costs of real estate, a big part of a supply chain cost, a major part of the supply chain cost is the fixed cost, purchasing land, putting up the facilities, and making sure that what is important in terms of real estate quality. It has to be close to all of these different places, right? So we know if you go to buy a house, some of you have probably heard this, what are the 3 factors that influence what the price of the house? Exactly, right? So the primary thing is location. Access to transportation, access to high quality labor, an area that is livable. So all of these factors equally influence facility location. Now, obviously, in some contexts, the influence is heavier. So, for example, a lot of people would like to live in the southwest and the southeast because it's warmer, and that's where you see those regions growing faster than many regions in the north. Okay? You see clusters of manufacturing around the country. An important cluster of manufacturing is in the mid-Atlantic and Midwest, right? So you see those, and an important driver of that is you have access to high-quality labor. Why is high-quality labor? You see, schools like West Virginia University that were land-grant schools that were established in the mid-19th century with the Land Grant Act, and they provided access to a steady supply of high-quality labor. Then you have international factors such as duties and duty drawbacks. So we'll get an opportunity to look at some case studies, and you'll see that duties are an important factor in deciding where companies locate globally. And these are variables that are also included in network design optimization problems because they add on to the cost. For example, of moving goods across the border. You move a component across the border, you pay a duty. If that component goes into an assembly of a final product, and that product stays in that country, that duty is added on to the cost of that product, and so customers have to pay. Right? What is the current discussion of trade wars about? It's about that very issue, right? It's about duties and how it's going to raise the cost for American products abroad and foreign products here in the United States. And of course, eventually, the consumer is going to pay the price. Then what happens if we re-export that item, that product that has got that component that has been assigned a duty to it? Then that's called a duty drawback, where a percentage of that item, or the duty on that item, that component, then gets paid back to the manufacturer for re-exporting that. And one of the reasons why the governments do that is it is an incentive to drive export. Why do we want exports? Right? This trade gap that you keep hearing about? The trade gap is basically a measure of how much money we are sending out of the country versus how much money we are bringing into the country, right? So as long as we have a healthy generation of economic activity within the country, then you see that trade gap, a positive trade gap, always present. But anyway, so duty and duty drawbacks are a factor that are important in deciding where you locate. And one of the ways around duties and duty drawbacks is international trade zones, or international free trade zones, or free trade zones. So these free trade zones are where a country sets aside an area and says, any companies that want to locate over there, you can do any manufacturing, any assembling, and you can re-export that item without any duty. If you want to bring that item into the country, then you have to pay a duty for it, right? And that is an important incentive because now you allow industries to locate in your country, you provide employment, you provide incomes, tax incomes, but you don't provide any, or you don't get any revenue from duties unless those items come to the country. And if those items come to the country, usually the duties are lower, okay, because you also want to provide that company incentives to also distribute their products locally and have access to local markets. Okay, so just to demonstrate some of the complexities of how these factors influence facility location and gain an appreciation for how important it is for us to appreciate the fact that we have mathematical programs that can look at all of these variables simultaneously and come to a solution. We look at 7 of these factors and see how they influence facility location. So we know that freight rates are going to affect facility location, right? Depending upon where you are in the country and where your customers are, the cost of transportation is going to influence where you locate. We know that freight volumes are also going to influence where you locate. I mean, if you go back even to Weber's classification of industries, if the amount of freight volumes coming in is lower than the amount of freight volumes going out, then obviously you want to locate closer to your customer. But we also know that freight volumes affect freight rates. So already we have a circular logic over there where these factors influence each other, right? So we have to iterate to it if you're doing it by hand. But the nice thing is we have linear programs that do it for us. Then you have facility location that influences freight costs. You also have where you locate influencing the service levels, as we know. Closer to the customer, higher service levels. Your freight costs are going to affect your product costs. Simple landed costs. And then your service levels are going to affect your service volumes. Your sales volumes. So the better the service, the more business you get. But your product costs are also going to affect your sales volumes. And then in turn, your sales volumes are going to affect your freight volumes. So, clearly this is a complicated problem that is well suited for linear programs, and we'll learn how to do some formulation later on. I know you've been eager to learn how to do that. Several of you have asked me whether we're going to have binary problems, and I don't want to disappoint you all, so we'll be doing some formulation a little bit later on. But before we do that, we're going to look at different ways in which we can classify these problems. We can look at facility location in terms of a variety of different objectives. One very simple objective is by looking at what sort of fleet mix and driver mix we have. We can look at how many vehicles we have, what sort of drivers, and based upon that we can come up with different terminals that would be able to decide for us where our facility should be. We can also fix the number of facilities. Say we have 5 facilities or we have a budget for 3 facilities, and then we can go about understanding where we want to locate those. These problems can either be looked at as a continuous problem or a discrete problem, and we'll look at examples of both. Continuous problem being we can locate anywhere. Discrete problem means we can only locate in certain pre-specified locations. We can look at different time horizons. We can look at, say, for example, 1 year out, 2 years out, 3 years out, 4 years out. Typically, 5 years out is the longest you would want to look at. Sometimes people might say 10 years out, but typically you want to look at a certain time horizon. The shorter the time horizon, the more accurate it is, obviously, because everything else depends upon forecasts. We can look at different objectives. So one objective might be simply minimization of cost. Another one might be maximization of revenues, which again has to do with customer service. Maximization of profit, maximization of market share. We can also look at maximizing revenues and maximizing customer service and maximizing market share in different ways. We can look at another way of looking at market share is looking at how much of the market our DCs can access within a certain amount of time, which would be a proxy for how quickly we can get our product to our customer. All right, so any questions so far? I feel like I've been moving very quickly. Okay? Okay, so let's start by looking at a single facility. So we're given the number of facilities, continuous problem, which is where we can locate anywhere. So our objective is to locate a single facility to minimize transportation costs. Now, when we say a continuous problem, we're given an area. So think about the map of the United States, the contiguous 48 states. And we can, it's just a blank space. We can locate anywhere A problem with that is clearly our location might be on a geographic area that does not support our facility, right? Might be in the middle of a lake. But that's the basic assumption we make. We can locate anywhere. So we've already done this approach last year, right? Remember, it's called the center of gravity approach. It's a simple grid method. So we're going to look at that in a little bit more detail. So in terms of center of gravity or the simple grid method, there's only one factor that really affects the cost, and that is the linear transportation costs. And so the linear transportation costs are a product of the freight rates and the volumes. Okay? So that's your, and why do we call it linear? Sorry? Yeah, because it's constant, right? What's the other way of costing of freight rates? Sorry? So we have weight breaks, right? You've covered weight breaks in transportation management. So you have weight breaks, and those weight breaks are non-linear. Because for smaller breaks, you're going to have a much higher price. And as the weights increase, then you're going to have a much lower price. So there's this exponential drop in the cost. So usually, and even for some of our math programs that we can formulate, we can use nonlinear freight rates because we can use a nonlinear function if we use a nonlinear program. But for this method, we're going to assume a linear transportation cost. And what we're doing is we are trying to minimize our transportation costs across all of our locations for that single facility. So whether it's a facility that is getting in raw materials, converting them, and then shipping them out to DCs or customers, the total transportation cost is being minimized. Okay? So we minimize the transportation cost based upon the volume, the freight rate, and the distance. Now the subscript I indicates the location from which or to which we're shipping, okay, from that location. So a simple stylistic example of what we're going to do. So let's say we have let's say we have 2 suppliers, and let's give our suppliers a location here roughly, and let's say we have 5 customers that are located like this. Okay. So as savvy supply chain professionals, where would you say that we want to locate a warehouse that is getting shipments of finished goods from the plants and then shipping them out to the customers? In the center, obviously, right? So the shipments would come in from each plant and then go out to each customer. Okay, so there's a very simple formula that we can derive based upon what we just drew. If we consider all of these locations as being on a Cartesian plane, in other words, they all have x and y coordinates, right? And the x and y coordinates can then be used to find the distances, which will then be used to find the location of that red triangle as a warehouse that we want to use or that we want to locate in order to minimize our total transportation costs. Okay? However, there's a problem with this formula. What is the problem that we have to overcome with this particular formula that is given to us? So This formula is requiring us to provide information that we don't already have in order to calculate the location. So as inputs, we have the volume of the freight from each location I. We have the freight rate from that location I. We have the coordinate of that location X and Y for each location I. And then we have the distance from that location I to the facility that we want to locate, right? So what's the problem with this formula? Exactly. It's a tautological problem, right? It's a tautological question. We don't know the distance until we have the location, right? So that's circular logic, and we cannot figure it out. So a simple solution to this is to just cut off the d. Let's take out the distance, and then we have a heuristic solution. And this is called the simple grid model that we learned last semester. And then once we have the location of X and Y, then we can calculate the distance, and then we'll go through the next steps to see how we can find the optimal location. All right. Any questions so far? Okay, so let's do a simple example here. So we have the X and Y coordinates. So this is our origin 0, 0. This is our 0, 10 coordinate. This is our 10, 0 coordinate. So this one is 1, 1. This one is 2, 8. 1, 2, 3, 4, 5, 6, 7. This one is 6, 7, and so on. Okay, so you can see the coordinates of all of these locations are provided. So let's see here. 1, 2, 3, 4. Yes, that's 5, 7. I miscounted one. Okay, so we have these coordinates given to us. We have the volumes given alongside each coordinate, and we have a fixed freight rate, and the freight rate is fixed for all points, and it's $20 per ton mile. So then, from last semester, you know, it's a pretty straightforward process where we just draw this table in Excel, and we have the volumes, we have the X and Y coordinates for each point, and now we simply have to multiply the volume by the freight rate, which is 20. And then we multiply this by the X coordinate and the Y coordinate. Yeah.
Did you get back a couple of when I printed it made some weird symbols?
Hmm.
I don't know what it did.
Is it college printer?
Yeah. It's one upstairs in the room.
Sure. So to calculate the coordinates, then it's simply a matter of saying x is equal to 4200 over 1040 and y is equal to 4640 over 1040. And that gives us our x and y coordinates. Now this is without the distances. So when we plot the solution on our grid, then we get the solution to the simple grid method, which shows us where to locate our warehouse. So now that we have the location, we now must compute the cost. To compute the cost, we have to compute the distances, and this is easier done in Excel. So you can just plug this formula into Excel and use the x and y coordinate that we just figured out in the formula, and the xi and yi. You can see how it's used to calculate the distances, and then you take the total cost as the sum product of the volume, rate, and the distance for each I. So this simple grid method, as I said, is a heuristic solution, and we can improve upon this by using an iterative method. And this iterative method actually iterates towards the optimal solution, and this can be proven using simple calculus, where you can see that each time you plug in the new xy to get the distances, and then iterate towards a new solution using the current distances, you're actually going to keep moving till you see no improvement in a solution, which means that you have an optimal solution. So the steps of the exact grid method, which is the optimal solution method, is you start with a simple grid solution. So the solution that we just started off with, that becomes your input solution to this exact grid method. And then you calculate the x and y coordinates based upon the distances that you got from the simple grid method, and you keep repeating until the solution converges. So we have the original simple grid solution as x1 and y1. Then we go through and we calculate the distances, and then we now have Vrx over d, Vry over d, and Vr over d. So we have the numerator for x, we have the numerator for y, and we have the denominator for both x and y, which is Vr over d. Then we can calculate the first iteration of the exact grid method in the same way. We just take the Vrx over d over Vr over d, and that gives us 4.1. And then we take the Vry over d and the Vr over the Vrd, and that gives us y2. That gives us the first iteration of the exact grid method. Okay, so that's the second step, but the first iteration of the exact grid method. So we can go through this. So our first step is the simple grid method, 4.0, 4.5, and the cost is 44.82. The second one is what we just calculated, 4.1 and 4.4. And that cost, you can see, falls by 3 units. The third step, or the second iteration of the exact grid method, does not give us any improvement in the total cost or the location. So in this case, we only took 2 iterations of the exact grid method to come up with our solution. Now, obviously, in most typical problems of a real world case, you're going to see more than 3 iterations before you get the solution. In this case, we only had 5 points in our example, just to keep our computational simple. We had 5 points in our example in order for us to see a quick convergence to the optimal solution.
How many iterations usually is there in the real world?
So,
Just like 5, or is it like
if you take a 50 randomly dispersed location problem, then if they are randomly dispersed, then they're much easier to converge, okay? Because you're not going to see too much dispersion. If you start seeing clustering, also you're going to see a convergence easier. That's much easier. The problem becomes when you start having weights among the items that are extremely variable, and that's where you're going to see longer iterations. Can't really give you a number. It so much depends upon the dispersion and the relative volume of the weights of each of the locations, the nodes. So, typically, if you see, 50, so I generated this 50 randomly dispersed, roughly equal volumes, and the transportation rates that were on average about 1.6% between the optimal and the simple grid method. Okay, so you gain only a 1.6% improvement in your solution by increasing the number of iterations to the exact grid method. Okay, so there is, in some cases, again, it's a heuristic, so you don't know how close you are to the solution. Typically, you're going to see that the difference between the exact grid method and the simple grid method don't vary widely if the volumes are, there's a small standard deviation in the volumes of all the nodes, and there is a large number of demand and supply points that are equally dispersed or randomly dispersed in the space that you're considering. Okay? So that's the evaluation for the simple grid and the exact grid method. Even though you may not think of many real-world applications, if you're thinking of solutions, for example, with drilling in ocean drilling of in oil fields, you can see that if you want to find out where you want to locate your drilling platforms in relation to your the wells that you have, clearly it's extremely expensive to put in underwater pipelines. So you want to locate your refinery or your offshore platform as close to as many of the oil wells as possible, and therefore this would be a way of finding that location. When we do the network design, you will also see that the simple grid method or even the exact grid method is used as a starting point solution. Okay, so we introduce it into the problem as a starting point to speed up the optimization and to give us an optimal solution much quicker. So that's one way of figuring out how we can use the simple grid method in a real world application as a heuristic to speed up our network design optimization. So now we're going to look at a discrete set of facility location problems. So there are two sets. There's the K set and then there's the covering set. Okay? So there's two types rather. Shouldn't be confusing sets, because there's a problem that is called the set covering problem. So the two types are the K-type problems and the covering type problems. So the K-type problems is where we're given the number of facilities, the number of facilities is given as K. Whatever our problem is telling us, whether it's 5 or 6, that's going to be K, the number of locations. Now the K median is where you want to locate your facility that is on average minimally distant from all of the points in your problem. So you're trying to minimize the average, the total average distance from your facility to all of the nodes or all of the customer or supply locations in the problem. The K-center problem is where you want to minimize the total distance from your location to all of the other customers or supplier locations. So that's the difference. So if you think about constraints, the K facilities is the constraint, and for K center, you can see again your K facilities are the center. Now, for your objective, you want to minimize the weighted average distance. You can weigh the average distance with the total volume or the total units, or if it's a passenger problem or a retail problem, as we'll see next. It will be it'll be the number of passengers or customers that are traveling from one location to the other. With the K-center problem, our objective is to minimize the total distance. Now, for the covering problems, both the covering problems have a unique constraint, and that constraint is we want to serve all of the locations within a specified distance. Okay? So we have a unique constraint here. Now, the max covering problem has another constraint where we are given the number of facilities. So it's similar to the K problems, the K-type problems, where we're given a certain number of facilities. The objective for the set covering problem is to minimize the total number of facilities. Because here we want to cover all of the demand. So that's an important factor. Or again, we could call it another unique constraint, where we want to cover all the demands, and that's within a specified distance. With the max covering problem, our objective is to maximize the number of demands that can be covered. So all four of these can be formulated as a linear program. And even though you're really enthusiastic about formulating linear programs, I thought we'll just leave one to be formulated right now, okay? And keep the other three to be formulated in the next semester. Yep? Okay. Getting thumbs up over here, so that means it's, you're happy about that. So let's start with the K-median problem. Let's look at a K-median problem. And now, remember, this is the discrete type problem. So what's the meaning of a discrete type problem? The locations that you can potentially locate a warehouse or a K number or the K number of warehouses is given to you already. So you already know that you have these set of locations given to you. And those locations will be connected to each other. So you have nodes, the potential locations, and the nodes will be connected using edges in a simple graph. So think about an example where we have 5 towns, right? Might be somewhere here in this vicinity. We might have, for example, Suncrest, Saberton, Westover, etc., Fairmont. And you have a grocer that comes in, say it's Aldi's or Trader Joe's, or somebody who's not already here, and they want to locate their facility that is closest to all the customers. So remember, what is the objective of the K-median problem? Minimize the weighted average distance, right? So if, in this case, what would the weighted average distance be? It's the total distance traveled by all of the customers at any one of these towns, right? So we want to minimize the total average travel time of all of these customers. So an important result of a discrete K-median problem is that you're going to find the optimal solution only at the nodes of the network. So why is this helpful? Why is it helpful to know that the solution of the optimal solution to our problem is always going to be at the nodes of our graph?
Because the facility already exists.
Because the facility already exists?
The nodes represent facilities that already exist, or are they?
No, they are potential facilities.
You know it's not a lake.
Sorry?
So you know it's not a lake.
No. Yeah.
Where do you know like the distance and like numbers that are attached to each node, so it would be easy to find the minimum?
Okay. It's along those lines. Yeah. Yeah. Not quite it, but close. You're close. So it's easy to find the calculation of the weighted average distance at all the nodes. What does that mean? You can just enumerate the solution for every node, right? Remember the first thing that we started off when we did solution methods in not chapter 6, but in lecture 6. Enumeration was one method, remember? We enumerated all the different possibilities of locating 15 warehouses in 60 locations, and we said it will take close to 2,000 years. So we could do this in this network, but it won't take that long. Just one warehouse on 5 nodes, right? So we just check the cost on every single node, and we could come up with the optimal solution. Enumeration is as good an optimization approach as the simplex or any other algorithm that we have. As long as it's short and doesn't take up a lot of computing time. So the first thing that we have to do is we have to calculate the distance matrix. If this was a complicated graph, then what method would you use to calculate the distance matrix? The Dijkstra's algorithm, right? So luckily, this is a pretty straightforward distance matrix. It doesn't involve too much. So I'm going to write down my So I'm going to take the rows as my warehouse locations. And in the columns, I'm going to put my customer locations. And then I just put in my distances from each customer to each warehouse. And what I'm going to put on top of each customer location is the number of customers at that location. And then I'm going to draw another table again with the warehouses in the rows and the customers along the columns. And now what I'm going to do is I'm going to multiply each of those customer locations by the distance. And I'm going to produce that result in the cell below. So this, for example, will be 0. 3,000 times 1 is 3,000. 3,000 times 3 is 9,000. And so on. And at the end of it, I'm going to sum each row up. And then I look at the sum and find the one that has the lowest minimum or the lowest total cost. So now each one represents the average time-weighted distance, the average time-weighted for each customer location to arrive at the warehouse location which is in the row. And so by picking the minimum sum, I pick the store location that minimizes the average customer travel time to that particular location. Okay? Yes?
What if they're equal?
If they're equal, then you could choose either. Then there'll be other considerations that would come into play. You'd say, do you have a lower, I mean, this is only using one criterion. Remember all the different criteria, so then you would obviously. So step back and take into perspective a little bit. This would be one input into your consideration. When we look at retail, we'd see a more realistic example of how this would be one input into a scorecard. In our example, we only have, I think, 8 or 10 items. But in reality, you would have 25 or 30 or even 50 items that you score for each location, and this would be just one input. Okay? And of course, there would be weights for them, etc. Okay, any questions besides that? So, the obvious next question is, we did it for one location, can we do it for 2 locations, right? So, how do we solve the 2 median problem? One example is enumerate the solution for each node. You take the smallest and the second smallest. So in our case, we will take B and we take C, right? Cliff is saying yes? Yep. I say no. Right? So that is actually a suboptimal solution. It's always going to be a suboptimal solution. Okay, so you don't want to do that. Because what that is doing is that it's not taking into account, you need to take into account the location that you pick and then do it again. Exactly. So there's 2 ways you can do that. Either enumerate for each pair of nodes. And if you go to the lecture notes, you will see that there is a link that I put to an example that does just that. Okay, so enumerate for each pair of nodes. So go and do that. Or the better way to do it is to fix the one median problem, remove that from the solution, and then enumerate the solution again for the remaining nodes. Okay? Or really the best way to solve the problem is to write an initial program for us, right? And that's what I've been waiting for. Unfortunately, we'll have to get it to the next time, because I don't think we'll go through the whole thing this time, at least in an appreciable way. All right? So let's keep this for next time when we start doing network design. It's kind of appropriate that we start there as well. Till then, I'll see you on Thursday.